that function is?
Tanh.
And so that's a tanh, right? Tanh KL, right? Which is going to look like something like that, right? This thing over here, right? It starts out at 0, okay? And then when K is positive, it's going to kind of look like this, right? And it looks something like that on the negative, right? So if I want to know about, what the solutions to this will be, it looks like, as Kyle said, I'm only going to get K equals 0, right? But this actually depends on the sign of AL and A0, okay? And it turns out that if A0 is less than 0 and AL is less than 0, I can have basically this function is it's gonna flip, right? And so in that case, I have that this function looks like more like this, right? And so I get an intersection like something like this with my tanh function here, okay? So in order to see that in this case, right, I can define this function f of k, and f of k is going to equal this function here, right? So if the question is, when am I going to have sort of non-trivial solutions to that equation? That's not what I asked you to do. I just asked you to sort of work out this result as best you can, right? The relationship of the implicit relationship that gives you k. But if the question was, when do I get negative eigenvalues in this case, okay? If I take A0 and AL less than 0, okay, then f of k is going to be equal to actually k times the absolute value of A0 plus AL, k squared plus A0 AL, okay? And the maximum, right? So this function k A0 plus AL divided by k squared plus A0 AL, right? It's going to look like for if I have a tanh here, right? And I have the function coming in over here, then I can get, I think I can get, sorry, I haven't drawn this quite right. I can get two intersections with the tanh function in that case, okay? Because in this case, f of k, and I've run out of time, so I don't have time to show this, but you can use calculus to basically show that f of k is maximized when k is equal to the square root of ALA0, okay? That maximum is equal to this quantity here, okay? Which is greater than or equal to 1, okay? So there is an intersection, okay, at least at k equals 0 and at least for at least 1 k greater than 0. Basically, since tanh of KL is upper limited by 1 as k goes to infinity. You could get 2 intersections, but the point is that you're going to have at least one of these intersections, okay, which can lead to unstable solutions, okay? So if you're solving this problem, you need to be worried about that because you can potentially get solutions that are unbounded. If you're solving it numerically, right, you could have your solutions essentially blow up because I have a negative eigenvalue associated with my boundary value problem. That's going to lead to a positive growth term in my time-dependent terms, and then I have stuff shooting off to infinity. Okay. So why did I do this problem? Yeah, sorry, it's sort of a long problem to do just in class like this. Okay. But I wanted to get a little bit more into the kind of messiness that you have to deal with when you work with these eigenvalue problems. We saw that you're not always necessarily going to have explicit solutions. You're going to have to use some, reasoning kind of based on the shape of the functions in these implicit equations. That's fine, okay? But we were able to do that in this case, okay? And so what I'll do, I have just a short solution of this problem written up. It's just a book problem. I will pass that along to you, and you can look it over, and hopefully that will help you a bit on the problem they have to do on the homework, problem 5 in chapter 6. That problem is, it's not the exact same as this one, but I hope I'm giving you some insight into the kind of analysis that would help when you have implicit equations rather than something that you can solve nicely and explicitly. All right. Sorry, I talked for a long time. Are there questions about this?
So I think I understand that if we say that both AL and A naught are negative, then we have energy flowing in, and of course the solution grows unbounded. And if they're both positive, then it's flowing out, and we don't. That was the k equals 0. Did we go over the case where one is positive and one is negative? Like I feel like we should have like if their sum is negative, then it won't be unbounded. Did we talk about that? Did I miss it?
No, we didn't talk about that. But yeah, I think you have to take it case by case. And there may be a condition on AL and A0 at that point that tells you whether or not you're going to have a positive or negative eigenvalue. So in that case, right, I mean, you can look here and see this, like, where do they show up? They show up here, right? So it depends on, yeah, whether their sum is negative or positive, probably, right? But also it depends on where this function is going to peak in this case. And actually, I think if this, right, is a subtractive term, it's not, I guess it's not immediately clear to me where you're going to get that peak, right? Because you have to worry about, whether the function is going to peak below 1 or above 1. If it peaks below 1, then you may have a gap here, so you don't have an intersection, so you're not going to necessarily have a negative eigenvalue associated with this problem. Yeah, that's a good point. We didn't deal with that, but that's that's a good case to look at.
So we're saying there's at least one intersection when we maximize the function, or for any, there's obviously not intersections for all values of A0 and AL, right?
No, yeah, so the condition we needed is that A0 and AL is are negative, right? So as Sage was saying, that means you're sort of flipping the direction of the flux condition so that you kind of have a partial flux of energy into the system in that case.
Gotcha.
Yeah. Okay. All right. So that's enough for today, I think. On Monday, we will pick back up on generalized Sturm-Liouville problems. We'll talk more about sort of generalized Fourier series, not just sines and cosines. You could have sort of any, any type of function that serves to provide you with a complete orthogonal set. You can build a Fourier series for that. So we'll look more generally at what a Sturm-Liouville problem is and why that can give to us these generalized Fourier series that allow us to do separation of variable solutions to BDs. All right. So I'll see you all on Monday. Have a good weekend.
Thanks, Zach.
Thank you. Have a good one.